I've got a couple of these DC brush type motors out of RO water filters, and they run the pumps. They're very high torque motors. I suspect that they would make a very good generator, maybe in the 90+% range for efficiencies. And as you can see, they have a relatively low startup voltage, call it about 1.4 volts. And as you can see, when I load the motor, the amperage goes up, which is something important to remember when we're making measurements. But yeah, let's try ganging this motor over to this motor and use the second motor as a generator, and we'll measure the efficiency and see if it's any good. These are free. You can get them when the RO filter systems go bad. So yeah, I'm thinking about using them for a generator for like wind or water power, so this is kind of where I'm going with this. Let's take a quick look at our setup. Over here we have the power supply, which we're going to be using to drive the motor. It has volts and amps on it. I've got my link here between the two motors. This is just a piece of plastic tubing. I'm not sure it's going to hold up. We may have to change that out for a piece of pipe or something. Moving on over here, this is our DC motor that's going to act as the generator. Back here we'll have volts and amps, and then over here is all of our wiring that goes over here to the meters. So that's it for our setup. For our first experiment, let's just try measuring the voltage input to the motor and the voltage we get out of our generator. Now keep in mind that any loss is shared between these two, but I'm assuming that the loss will be roughly 50-50 because, well, it's the same motor. So, okay, let's start cranking up the voltage and see what happens. About 1 point some volts we get the first turning. Let's crank it up to 5 volts so we have something meaningful. At 5 volts, we're getting about 3.8, 3.9, so we're getting about a 20% loss. Not too terrible. If that means that we're getting 10% loss here and 10% loss here, that's pretty fantastic, because a motor or a generator that's 90% efficient is wow. Okay, at 10 volts, we are getting 8 volts, so it's about a 20% loss in the system still. Let's go to 20. That'll be an easy number to calculate. At 20 we're getting 16, so still, yeah, actually about a fifth loss and fourth loss. And let's just crank it all the way up to 30 volts. And at 30 volts, we're losing about 7.5 volts. So yeah, I mean, these are very reasonable. This is pretty good efficiency for a generator and a motor. Okay, so what we'll do next is we'll try to do something similar with the currents. I think I'm going to have to change my link here. It likes to pop off. I'll probably have to go with copper or something. Okay, moving onward. For this round, I've made some necessary changes. I swapped out the plastic tube I had coupling these with a piece of copper that I've mashed down on each end. I've added a little flag so you can easier see when the motors are turning, and yeah, that's about it. So let's see if this copper coupler can handle the amperage measurements. Okay, so what I've done is I've now connected this meter to measure amps, and this one is still voltage, so we'll start cranking this up, and we'll hope that our copper connector can handle it. It does make for more vibration. So at 5 volts we're getting 2 volts over here. We're getting 20.22 over here, 0.175, so roughly the same losses between the two. Okay, let's crank it up to 10. We're going to get some more noise, but can't be helped. Okay, so at roughly 10 volts, we're getting 3.6 volts over here, so that's a significant a loss, and then we're getting roughly the same amps, which is a good thing. I'll have to measure the proportion and put those on the video and see if our proportion, our total watts lost, is the same. And we just had a failure. Okay, I have to go fix that, and then we will come back and try again. Okay, and resuming. I got a cable connector down in here now, and remind me not to stick my finger in there because it'd take it right off. Okay, so we're at about 20 volts and back to about 6 volts here, and right there 1.39 amps, call it 1.4 amps. Let's crank this thing a little bit more. Hopefully it won't fail again on me. I'll put the wattage equivalent on here when I edit it. And at 30 volts, we're getting 30 volts input, 2 amps input. I've got a connection burning, 7.3 and 2.3 amps. Time to shut it down. Oh yeah, nice aroma of burning insulation. Let's look at our results. I ran this several times where I started up the motor and kind of got an average of where it would start, and it was roughly about 1.4 volts at about 0.1 amps, and that was to overcome the mechanical friction of the two motors, because remember that at this point the second motor was not under load, so it's pretty much all mechanical friction here. And as we did throughout the whole video, we're assuming a 50-50 split of losses. Now, I think that's a reasonable assumption. You know, it's rough, but it's probably reasonable. So each motor was losing 0.07 watts in friction, which, you know, that's not too bad. Okay, so let's look at our results. We won't go through all the numbers. We'll pretty much just compare watts against watts. So at 5 volts, we had an input wattage of 1.5 watts and an output watts of 0.348, which is an efficiency of only 23%. Yes, that's not the 90% I was hoping for. Okay, at 10 volts, our input wattage was 5 and our output wattage was 1.7, giving us an efficiency of 37.3 in the whole system. Of course, we got to remember this is for the whole system. At 20 volts, our input wattage was 24 watts, our output was 8 watts, and our efficiency was 33.3%. Okay, going down again, and then 30 volts input, we had 60 watts, almost 61 watts. Our output wattage was 17.23, and our total system efficiency was 28.4%. Okay, so our system average is 30.5%, and that means our system average losses, now this is the whole thing, this is both the motor and the generator, 69.5%. If we do 1 minus this number, we'll get this 30.5%, so these are complementary. So the efficiency of the motor, of one generator, was 61%, which, okay, it's not 90%, but given that these are free and, you know, for DIY experimentation, okay, 61% is not too terrible. The lessons I've learned by running this little experiment, I wanted to believe these motors were high efficiency, like 90%. That was my gut feel, and my gut feel was influenced by what I wanted. Commercial DC generators have efficiencies of over 80%. That's common at 90%. Our finding shows a maximum of about 60%, 61%, which is not terrible for a DIY project. You know, it's a good starter thing. If you're just going to run a rough experiment, you're going to put together a wind project or a water project or something, okay, you don't have to invest any real money in it and you can get some results. But another lesson I learned is reality divided by gut feeling. Yeah, you get infinite variance because gut feeling is not reliable. And another lesson I learned is that you use bigger wires than you anticipate so that you don't get a smoke event. On some of my frames, you can see smoke rising up over on this side of the video. And a final note, few online sellers of these small DC generators, almost none of them. I didn't find any of them that listed their efficiency. So if you're going to, need to test this to get some idea of efficiency, this what we did today might work out for some of those generators.
Well, that's it for our experimentation of using a DC motor as a generator. Hope you found it useful and interesting in your home DIY electronics projects.